The class of methods I'm going to present is a bit different from the usual flavor of methods that you might have seen earlier this week. And it is often associated with this big notion of local pattern discovery or also exploratory data analysis. And so generally, the agenda for this talk is I'd like to give you a bit of a methodological introduction, and this would be very abstract and pure as to not block your imagination with concreteness. And then we have two material science examples that are actually taken from the second publication there in the references with Brian Goldsmith and the other colleagues from the FHI theory department. And what's important is that these applications you can try afterwards out yourself in the hands-on session. So here's really for the high-level overview mostly, and then later on we can also dive in deeper, and you can also ask more questions during that session. But also, please feel free anytime, since this is a summer school, so I think it's appropriate to have an interactive lecture. So if something is unclear, please jump right in with questions. I'm trying to notice your arms when you're waving. Okay, so for the big picture, which is good to get right in the beginning, as already mentioned also in the first talk, and I think perhaps also a couple of times earlier during this week, generally when we talk about data analytics, really we can talk about two different things. And many of the methods, they're somewhere in the intersection and can be to a certain degree used in both of these areas, but sometimes we have to make choices that are motivated by the underlying use case that we're working on. And also in the keynote, we were talking about, or just in the beginning, you showed the self-driving car. So apparently, we cannot get by in any talk without this example. It's perhaps a prime example for this one direction of applications that we can work on with statistical learning. And this is predictive modeling, where our goal is ultimately to build a very accurate prediction machine that afterwards can be used autonomously without having humans in the loop. Ultimately, so that's actually often the underlying goal to get rid of the human. So, and that the self-driving car is perhaps the prime example. But also, if we think about high throughput screening in the chemical domain, that would be another example. We're really just interested in having an as good as possible model to predict our energies, and the mechanistic understanding is not the primary goal. And in contrast to that, on the other side of the band. We have exploratory data analysis, where it's exactly the opposite. Here, we do not want to get rid of the human, but to the contrary, we really prepare models, insights, patterns, automatized findings, but in order to present them to the human afterwards, in order to develop mechanistic understanding and really have an explicit representation of effects that are take place in our data set between the different variables. And in the subgroup discovery, we are decisively in this direction, and this is where we do our trade-offs. So it has been already mentioned that one of the known trade-offs is the accuracy simplicity. So if I want to be able to interpret my model afterwards, I might make some concessions when it comes to how accurate it is. Then this rules out a couple of methods perhaps already with high nonlinearity or other black box mechanisms like kernel functions. But there's actually another implicit trade-off that is not so often talked about, and that is this trade-off between generality and locality. Because another distinctive feature between these two sides is that in the predictive modeling case, like in the autonomous driving, I have to be able to make a prediction for every given sensory input. Similar for my high throughput model, I want to predict an energy for every material that comes in. The prediction might not be as accurate, similarly accurate in any region of the data space, but ultimately the goal is that we are able to do this automatized prediction. In contrast, in the exploratory data analysis case, I am actually allowed to say I don't know sometimes, and I can focus with my automatized observations on those areas of the data space where I have strong, clear trends. So that is this idea of locality. So to a certain degree, we're allowed to sacrifice generality in order to focus on the areas where with high confidence we can say something about our data domain. Now, how does this look more concretely? In this example, so I'm starting with the basic classification setting here. So generally, our setup would be we have a sample of a potentially larger population of our interest. And in our case, this would be materials. And for each of these materials of the members of this population, I can measure certain variables, certain properties. So first of all, there is one, the one most important property, which I call the target variable y. And in our case now, in the starting case, this would just be, this would take on a value, one of a fixed small set of possible classes in this basic case. And additionally, I have a couple of descriptive features. So in this example, I have two numeric descriptive features, x1 and x2. And the target variable is this distinction between boxes and circles in this case. Now, if we have the mindset of predictive modeling, now we would like to have a model that for the complete space tells us where would I find boxes, where would I find circles. As you can see in this example, this looks fairly complex to be characterized based on these two predictive features alone. Anyway, if you start with this mindset and you also keep interpretability in mind, then the prime technique that is usually used in the data analysis community are decision trees, because they have this nice human interpretable shape of my decisions, why I classify certain regions in a certain way. And in this example, the optimal decision tree of a depth 2 looks in fact like this. So first I would make a decision splitting on the x1 axis, splitting the data space into two regions, and then I have, depending on where I go, if I go to the left side here, I would have a second decision where I split based on x2, and then ultimately I end up with this, I partition the space into these rectangles, and then in each rectangle I have a majority class which I can use to predict the label of unseen or new examples, or just to describe the data space in the first place. And obviously here, this is fairly limited in terms of its effectiveness. I can use deeper decision trees to have a more refined partitioning. But it actually turns out if I do decision tree induction in a technically sound way, I have to do something which is called structural risk minimization. And that says if I go and build more and more complex trees, actually the generalization ability or also the performance on unseen data will deteriorate because of the high capacity of the hypothesis class. So it actually turns out that if you do it in a sound way, the level 2 decision tree is actually already optimal in that sense, that having this trade-off of accuracy and robustness. And now you can see that while you have a certain accuracy which is not very high, you predict with 60% accuracy or so in the example, actually some local regions in the data space which are highly interesting in a way, because here, as you can see, we have only circles and here we have only boxes. The decision tree does not represent these regions at all. Why? Because it has to take into account the global picture at all times. And this is the optimization function that is optimized by it. So here we actually jump now in with subgroup discovery and we say, okay, wait, let's change the underlying objective. We are interested in these local observations. Let's neglect the global accuracy and focus on subspaces of the data space and try to automatize, in an automatized fashion, find these subspaces where we have actually strong observations. So the way this looks like is actually very similar when it comes to the model language, to the decision trees. So the way we do this is we fix basic propositions, so simple Boolean functions that are formulated in terms of our input features. In terms of the numeric input features that we have here, these would just be inequality conditions. Okay, so my one proposition could be, okay, x1 is less than that and that threshold, or x1 is larger than that and that threshold. And I do so for every of my variables. And in this way, I can also mix in other measurement types, like also numeric measurements, non-numeric measurements, where I just would have equality constraints. If I have counting variables, I could have algebraic features, number theoretic features, and we also see that afterwards. But that is really also part of the input design, just as it has probably been mentioned that the feature design is very important also for the materials, not only for the materials applications, for any application. Also here, I have to make sure that I design these propositions in a physically meaningful way that have some connection, some plausible connection to the domain. And then after this step, I say, okay, now I consider the selection language for local data regions, which considers all possible conjunctions of these individual basic propositions that I have set up. And in this way, I end up, in this example, with regions that I can describe with these selector functions that are similar to those regions that I can actually describe with a decision tree, but now we can do so in a decoupled way. So by forming the conjunction between these inequality conditions, ultimately I can also carve out these axis parallel hyperrectangles that we have seen before. So now it's only rectangles, but usually in reality we have a lot of variables, so it would be d-dimensional hyperrectangles. And here you can see some two example subgroups. So this would be now subgroups or subpopulations. So a subgroup ultimately would be the combination of the selector function that I have in the form of this conjunction plus the model observation that I have within that subpopulation that is described. So I have this intentional description of the subpopulation by the formula, and then this what I would call the extension of the subgroup. And these two are relatively random just to illustrate the kind of language that we're using. And ultimately we want to find useful subpopulations. So how do we do that? We set up an objective function that very generally in all the possible variants that I'm going to show you can be written as a product of the coverage. So the described subpopulation would be here Q, it would be the subset of the sample that is selected by the selector. And then I consider the product of the coverage, and usually I have some weighing parameter here also, but we can ignore this for now. Coverage, and I have, so the coverage would measure the relative size of the selection, while I am willing to sacrifice some of the generality. Generality is still a good thing, so I'd like to have local observations that are as general as possible, but not more so than they are. And on the other hand, I like to have as strong as possible effect in that subpopulation on my target variable y. Okay? So as I already mentioned, the coverage would just be the relative size. When it comes to the definition of effect, this highly varies depending on what kind of effects I'm looking for, what kind of patterns do I want to identify. And in this case, where I have the multi-class or multinomial target attribute, one way to define the effect is to say I am looking at the relative reduction of Shannon entropy among the labeled distribution. So I have a global distribution of circles and boxes, as in this example. It would be 50-50, so that would have a Shannon entropy of 1. Okay? So that would be the HY in the whole sample S. Okay? And then in my subpopulation, I can again compute the Shannon entropy if, like in these cases, the distribution is actually pure. I only have circles, I only have boxes, I have an entropy of 0. So that would, in this normalized formula, evaluate to 1. I have the maximum effect. And in the same sense, if I had no change in distribution, it would be effect of 0. And we interpolate linearly between these two things. And as you can see in this motivational example, we actually select exactly these highly pure regions with this method. So one other thing is, whereas in the decision tree example, or generally in global predictive machine learning, I'm always optimizing one model. In this subgroup discovery optimization, I have this selection language, and ultimately I can rank all the possible selectors that I have according to my objective function. And I can also select multiples because they talk about different parts of the data space, perhaps talk about different regimes, underlying regimes of the material space, and they're actually complementary, and very often I'm interested in more than one model. And if I'm lucky, they can actually be patched together to result in a global model. And this is exactly what we see. Okay, first of all, to check that, yeah, we did not represent these patterns, but we have seen this already earlier. It's exactly actually what we see in the first application example, and now I'm, yes, please.
Before going to the example,
yes.
to go back to your, can it happen that you have two subgroups which overlap? Or
Yes, yes, you don't exclude this in any way. Actually, this is part of the problem if you look into more advanced methods, that very often if you have one region where you have very strong effects, you might get a lot of alternative descriptions for them. So you have actually to take into account redundancy among the selectors, like also semantic redundancy in the descriptors, but there are ways to rule that out. And then sometimes you have to do even more. You have to do like a projection pursuit approach that you say, okay, in my first subgroup I already covered this part of the space. Now I'm going to discount the coverage in that part in order to, in the next iteration, have a higher incentive to cover other parts of the data space. So they can, which is on the one hand a feature, on the other hand it can also turn into a problem that one very dominant region where you have very strong patterns might actually hide other parts of the data space where you still have good patterns, but not as good as in the first region. But then there are techniques to address that as well. Yeah, in the first example, which is again the by now well discussed octet binary semiconductor examples, actually that is a case in where we can actually relatively easily find subgroups that are complementary, that actually have no overlap by chance, and by chance I guess it's due to the relative simplicity of the problem with only 82 data points. That are very complementary and can actually be put together into a global model. But that is something that we can see it can happen, which is obviously then a good thing. But we're actually a bit more robust in cases which are more complex and where, given the features that we have, it's not possible. We can still end up with some observations in the space that are still useful without leading directly to a complete crystal structure map, for instance. But in this case, it actually is even a crystal structure map in the end, as it turns out. So the data set is well known by now. We have this population of 82 octet binary materials. So they are represented by the A component and the B component. And for each of them, for each of these two components, we have as features, first of all, the basic features, which are the basic atomic properties of either of the components. So we know here ionization potential, electron affinity, and the radii of the various orbitals. And then we have these algebraic combinations of the feature. And in Luca's PRL article, there are all the considerations as to which of these combinations should be considered in order to have a physically interpretable feature space. And here we just take over these features, and we also use them. And then here is the visualization in the two-dimensional descriptor that has been established by the lasso method. And I skipped over this. So obviously, the target variable that we're interested now in is again, we want to predict if the material has an affinity for the rock salt or the zinc blende crystal structure. And so our target variable is now the sign of the energy difference between the rock salt phase and the zinc blende phase of the materials. So I have generally a zinc blende class and a rock salt class resulting from that, and running the subgroup discovery algorithm reveals as a first subgroup here this zinc blende group identifying these materials, and it does so not based on the features that we have here, and I'm going to compare this in a second, but only using a conjunction of two basic propositions about the radii. So we have the difference, the absolute difference in the p orbital radii between A and B less than 1.15 angstrom is the first condition. Second condition is the s orbital of the first component has to be smaller than 1.27 angstrom. And this selects these 40 materials, all of which have a zinc blende affinity. So we have an effect of 1 because the label distribution is, or the class distribution is pure. And also we have a fairly large coverage of almost 50%, and particularly selecting 40 of the 41 materials which have the zinc blende affinity. Now, as I mentioned, we can look at two more subgroups in that list, and it turns out that the first rock salt group that we find actually nicely complements this first subgroup, and this is also interestingly defined on the same features. So these are all very good outcomes in that sense, and so we can almost select the whole complement. So we get 39 of the 41 rock salt affinity materials, and then if we patch this together, we actually end up with a complete description of almost complete description of the space. So if I talk now about local models, it's actually very global. We actually only rule out 3 materials about which we can make no prediction, and then it turns out when we look into these materials, they actually have a very, very small energy difference of less than 0.05 electron volts. So these are reasonable exceptions for my global model. Now, to see, like, if I plot the two subgroups in this space, which is designed in a way to have a good linear function as a separating hyperplane, the subgroups actually don't have a very logical shape. But now, actually, what I did here, I discovered a new representation only based on the orbital difference here and the orbital radius of the A component. And if I replot this, I end up with this thing, which I can consider as a crystal structure map. And here, we have really these, as I said, these, in a way, these axis parallel hyperrectangles which demarcate the blue group, the zinc blende group, and the rock salt group. And you can see that the space is different. You get different results because you ultimately have a different hypothesis language. Now you don't, like in Lasso, you look into the linear separating function, and here we have these boxes. So this determines why we end up with different descriptors in the end. Okay, so this shows nicely how local models can then ultimately also use to create global models if you patch them together. With this, I think I'm using already a lot of time. I'm not sure how much time I should use. 10 more? Oh, that's okay. But anyway, we have more time afterwards, so if I now get a bit faster, I guess that will be okay. And ultimately now what we're going to do is we generalize this first setting that we have identified. So now we started with having just a discrete set of possible target values, and now we generalize. First thing, we go to the regression setting, so we have a real value target variable. So for instance, we could directly investigate energies, right? And so the Kriging has already been mentioned, so there would be one thing now to do. Again, if I go back to the predictive modeling mindset, I could use Kriging or Gaussian processes, which is an alternative name, I think. And then I could learn a smooth function, now in this example now the target variable is now the y here on the numeric axis, and I have also put in again circles and boxes, I think, to have at least 2 descriptive variables at my disposal. But I already mentioned that I can mix types of variables, and x1 is as before. Now in this example, the Gaussian processes would result in such a smooth function, which well, arguably, okay, describes the data in some way, not very accurate, with a high insecurity, high error bars. But more importantly, again, not very interpretable when it comes to mechanistic understanding, because now our model is actually given as a linear combination of 200 kernel functions centered at the training, at the sample points, and so it's ultimately represented by the similarity to all my training examples. So again, I don't have really interpretable abstraction, and explicit representation of what of the input features is really important to determine a certain y or output value. Okay. So again, let's use the subgroup discovery trick instead. We use the very same considerations as before. We define this language based on basic propositions, and I can again optimize the combination of coverage and effect. Now the only thing I have to do is I have to change the definition of the effect. Now I have a bit of more choices because I have this numeric quantity and the different effects that I can consider, and there's also this consideration actually of Pareto optimal optimization here, because one, I might be interested in actually very outstanding y values, or, and that is perhaps more basic, and that's the case I'm going to focus on here, I am looking for effects that reduce the error or the dispersion in the value distribution of the y value. So I'm ultimately looking now for subgroups that can, where the target distribution can be described well by a constant function, okay? Where the constant function, which is the most simple model that you can imagine, where even that most simple model works well. Okay, so the way to formalize this is just to say, as before, I looked at the relative reduction in channel entropy. Now I just look into the relative reduction of the standard deviation of the target variable. And yeah, running this in this example yields this. This region is arguably a bit small, but it's highly accurate and has actually a good prediction band, where I can describe, so here I have this connection, the x1 value is large, the class of the x2 variable is a, and then they're all lined up here on this constant line. Okay? So this is now the intuitive or the didactic way to do this. Now let's look into our second application example. And here we change the data set a bit, or we change the data set completely. Now we have a different population that we investigate. And this is a much larger population in total, and we only have a sample of 20,000 of them in the end. And the population is small gold nanocluster configurations. So we have various sizes here from 5 to 14 atoms. And we are interested for now in the numeric quantity of the homolume energy gap of these clusters. So here I plotted this variable against the overall stability of the clusters. And I'd like to discover, again, regions where I can predict this property fairly well with a constant function. And I like to identify these regions by just the geometry of the cluster. So now we have a homoatomic structure, so we have a bit of we have to find a different feature representation. So what we're doing now is we're mapping these geometries to a fixed feature table tabular representation. And the way we're going to do this is we're just counting we're counting how often atoms in the structure have a certain number of bonds. Okay, so we have this distribution of how many neighbors does an atom have. So this is a graphic explaining this for this structure. So we have 3 atoms here that have 2 neighbors, 1 that has 3 neighbors, and so on and so forth. So I'm getting this distributional representation of the geometry, which has the advantage that it is translation and rotation invariant, which is already meaningful from a physical point of view because the properties should not depend obviously on the position in space. Okay, and then in addition, I also have the number of atoms. I have, if it's a 2D or a 3D structure, and I have certain derived features based on this coordination number. And the first thing that we can, this is actually mostly academic introductory example, is I can rediscover the insight that if I select all the structures that have an odd number of atoms, thus they have an unpaired electron, they have a very small homolumo energy gap. So this is makes sense physically, and this subgroup discovery based on the definition of coverage and the effect that we have chosen would discover this fact again, and would have a coverage, very high coverage of 50% of my material space, and have almost maximal effect again. And also a shifted mean if I would change the effect definition. Now to a bit more complex example where I need more complex descriptors in the end. So far we saw actually very easy descriptors most of the time. Is now I change the target variable, and now I'm going to predict the van der Waals energy, so non-local dispersion energy. And here is the global picture again of this variable. And we can see there's some clustering structure here, so there seem to be different regimes in that variable among my sample of 20,000 clusters. So could we take out individual of these clusters? It turns out that this representation is not lossless. We can't completely describe the physics of the domain here, but we can actually fairly accurate select individuals of these clusters, and depending on how I do the trade-off between size and the definition of effect, I could actually go around and find different these various clusters here. But this one, which is fairly large and has also an increased mean value, can actually be identified by this rather complex, but I would say perhaps still interpretable subgroup descriptor. We say let's single out all the gold clusters that have between 8 and 12 atoms, that have a large number of atoms with 2 bonds. So I have this, this ring kind of aspect in it, and not too many with 6 bonds, and at the same time which are not too compressed, so the radius, so this is the radius of gyration, should be high. And then we select this region here where you cannot really describe it by a constant function, but you really focused on one regime with a much smaller standard deviation at least. Okay, so the effect here is 0.68, and you have selected 20% of your input configurations with this. So you still have a fairly large group where you can say something happens here with respect to the van der Waals energy, and then you can obviously hypothesize why that is and investigate further. Okay. So now, very fast, just final generalization of this. So far, we only looked into one target variable, but we're in no way restricted to do that. In the final example, let's say we have 2 numeric target variables, and that you could play on this game, obviously, but like with 2, we can already ask even more interesting questions. We can ask, what is the relation between the first and the second target variable, and how does the relation of them, perhaps in local regions of the data, changes when I bring in subgroup selectors, okay? So in this example here, if you fit like now if you change, say, a relation between the variables, let's formalize that by Pearson linear product moment correlation. You can see that globally you have this picture that you have a fairly visible linear positive trend. And now I would define effect by change in the Pearson correlation coefficient. And then it turns out that, again, here I have this one Now I have only one descriptive feature, so that's a bit toy example, obviously. But in this constructed example, you can see that you can actually use this to identify these subpopulations. We actually have the inverse linear trend between the variables. So something interesting is going on here when it comes to the relation. And again, in the second application of the GOAT nanoclusters, we use this, and something that you can also try out afterwards, to investigate the relation between the stability of the configurations and the chemical hardness. You can see the global picture is well, fairly undecisive, but you can actually, with subgroup discovery, identify the subgroup of GOAT clusters with an even number of atoms, again with some feature on the coordination histogram, and with a low van der Waals energy. And if you restrict your attention to this subgroup, then it turns actually out that you have a fairly expressed negative linear connection between the two variables, and the most stable configurations are also the chemically hardest, and also in the non-minimum energy regime, actually you have this continuous linear trend between these two variables. So you go from a not very correlated situation in the global picture to the correlation coefficient of a minus 0.81 in this subgroup. And so now you can wonder why in this regime it is so that there's this connection between the stability and the hardness. Okay, so that's all for the introduction. As I said, afterwards we will have the hands-on session, and all the examples that I've shown to you now, and also more variants that you can try out with different target attributes. You can do so with our interactive tutorial that we have set up in the tutorial section in the NOMAD Analytics Toolkit. Thanks.
Thank you, Marie.